All right, so here I'm going to record the lecture in several parts. I've been meaning to do this for timing and for content. All right, so there's Gear Class 4, where we're doing Gear Basics 2. Today we're going to deal with gear train, kinematics, and forces. Okay. So in section 1313, we introduce something, well, we call them gear trains. And we introduce something called the gear train value that represents the overall speed ratio, right? So for each stage of gearing, the number of teeth, the ratio of the number of teeth are going to be inversely proportional to the speed change, right? Just as we saw with the basic kinematic relationships for a single stage of gears right here. Let me see 1 second. So we know for a particular gear, right? I'll put it up here at the top. That if we have a ratio of teeth, let's say, and by the way, quite often for whatever reason, when doing gear trains, it seems that Shigley does this. I've seen a couple other books do it. They don't bother with number 1 as the gear for whatever reason. So we're going to call gear, the first gear here, gear number 2. And so the number of teeth are capital N, and the RPM is going to be lowercase n. So if you have a gear ratio of N2 to N3, as we're just dealing with this stage right here, it ends up being inversely proportional. So the RPM is going to be the inverse right here, right? So 2 on the top, 3 on the bottom, 3 on the top, 2 on the bottom right here. So that what we're left with here is that when we're, for a single stage that we have, if we want to find out what N3 is going to be, it's going to be equal N2 divided by N3 of the gear teeth times the input RPM. So here's output, this single gear stage right here, times the input right there. So what we want to look here is the basic idea is that we have driving gear over driven gear, right? So that's the thing to kind of like use as the mnemonic maybe, or the thing to go. So also something we should know, that each time we have a stage, the direction reverses, okay? We can also, if there's ever any kind of question, I find it's easy to draw an arrow coming down, and then you could almost think of your hand getting, and this is really weird, getting your hand caught in there so that they come in and merge and come downwards, right? So there's a reversal at each of these stages. And some stages, right, we're going to see don't achieve anything because of the way things are going to cancel out. All right, so maybe I'm jumping ahead here, but we're going to introduce this idea of the train ratio right here, where we're going to go from each one of these things and we can put them together. So if you take a look at this train at each of them, and you were following this same logic right here, we would say we want to have N6 as the last one. And so we said N6. How do we get to N6? Well, what we do is we take N2 divided by N3 times N3 divided by N4. And now N4 doesn't drive anything, but it's connected to the same shaft as N5, right? So N4 is not driving anything, it's being driven, that's all. So now when the next one we go, we see that N5 is driving N6. And then we would multiply that whole thing by N2, right? Here's our input and our output. And each one of these stages is going to cause a reversal. Okay, we have to be a little careful with this when approaching it. We're going to come up and we're going to see when we have planetary gears, so we can have internal gears, right? So we have gears like the ring gear, and there's teeth on the inside, and gears roll onto there. That's not going to be a reversal, so we have to just be a little careful. So sometimes I try to avoid just saying, okay, negative, negative, negative. We would predict by saying that for every stage is going to reverse the thing, and we could give this thing a negative sign right here. So that we could say that each one of these, let's see, I'll try to make enough gap in there so I can put a negative sign. We have negative, negative, negative in the multiplication, so that the output of the thing is going to be some value times the RPM, and we're going to based on this, we're going to predict that the output is the opposite direction of the input. And so if you do the same thing as I did with my hand here, where we're looking to see where here's my hand would get stuck here, okay, well then this one right here is rotating in that direction. So this one has to rotate in that direction because my hand would get stuck right in there, which makes this thing rotate in this direction as it's already drawn, which makes that rotate in that direction. And now we can see. So here's a clockwise input, here's a counterclockwise output, so that negative is going to be correct. So what we refer to this thing is the gear train ratio, right there, that gear train ratio. And we could define the gear train ratio as being the product of the driving teeth, right? So we multiply all the numbers of teeth that are on each gear that is acting as a driver, and the product of the driven teeth. And you can say that each stage is negative, so you could or maybe it's better to just double check yourself, because sometimes we could have a more complicated setup where we have internal teeth on like a ring type of gear where they're and that does not reverse. So because we're also going to use this same product rule kind of idea when we go to try to figure out planetary gears. So this train value E. So a lot of times, so this right here is equation in the book 1330, right here. It's also written as, we can also just use this, quite often we'll use it as the RPM of the last gear, or of the last shaft, is equal to E times the RPM of the first, right? And that's going to be equation 1331. Let me pause the video for a second. I want to get my book out. Here we see the thing that I just referred to as being the in section 1313, and we can also see the gear train ratio, and they were talking about the negative right in here. So you can see here's our gear train ratio, and here is how we apply it to figure out the speed reduction. Or increase, to tell you the truth, because it will work that way too. An important consideration that we will want to make when looking at arranging gear sets, right, is the location of the input shaft and the output shaft, or the shafts relative to one another. And that's going to be, it's an interesting thing to do here. We could say that, like, maybe we, in a particular arrangement for something, we will have, let's say this is the input shaft. Well, maybe we want it to be on the same side, right, as the output shaft. And perhaps we want it to have it, they need to be this distance apart, right? So we would purposely pick the number of gear teeth. We would know what overall reduction that we would want to have, and we would pick the number of teeth, and well, we would also have to pick the pitch that we're choosing right there. But that combination of the number of teeth and the diameters of the gears are going to change what the center to center ratio distance is for each of these, and that'll determine the location of the thing. So when designing a gear train, it's not only the amount of reduction or increase that we want to have, it's also the arrangement that we have to kind of work through. An important thing to bear in mind, right? So here's an important concept here, is the practical max ratio is 10 to 1 or 1 to 10, depending on which way you're going down. And so it's just because it's impractical to get, you're going to have a very, very, very small pinion input and a very, very, very large 10 times the size output gear, right? So input gear to output gear. So you have to break down, when you have this overall train ratio that you need to have, you need to break it down in practical steps, and then none of them can be more than 10 to 1. So somewhere really somewhere like in the 5 to 1, 6 to 1 ratio becomes kind of more practical, but like overall 10 to 1 is like that's really the outside bounds of what you would want to have. So I'm looking over my notes here. Let me just pause a second. Let me also reiterate why that why the number of teeth and the shaft distances apart are going to be something that we want to talk about right here. So that's that idea isolated right here. But it's because pitch is defined by number of teeth by diameter right here, right? So as you go to have, say, like if we're going to number this gear, I guess I decided to number this gear 2, this is 3, this is 4, and this is 5 right here, right? So the distance that's between 2 and 3, right, that center to center distance is going to be D2 plus D3 over 2, right? And then the center to center distance that's going to be here between this shaft and this shaft is going to be D4 plus D5 divided by 2, right? So when going to go from the distances apart right here, what you want to try to figure out is you'll see that, like, you know, if we have the overall distance that was going to be between there, we could see that it's going to be D2 plus D3 plus D4 plus D5 right there, right? That's going to be that center to center distance that maybe I would say was right here to the thing. But you could also see that all we would need to do here is also say that we could we could also say that N is equal to PD, right? Or we could say that D was equal to N over P. So all we would have to do here then is say is 1 over 2P, right, is going to be N2 plus N3 plus N4 plus N5, right? So now for like a particular constraint that we have a relation here that we have to maintain. That's as soon as we pick out what the pitch is going to be, that it is a variable perhaps that we have, but there's a certain amount of dependence of that pitch we'll find on stress, right? That it's going to be advantageous for us to pick with regards to stress a particular pitch, or to keep it down to a certain number. So here's like a constraint that we have when we're trying to design. Another desirable trait often is to have the input shaft, let's say, I guess this is going to be the input shaft, and the output shaft, to have those aligned with each other. That's a nice thing to have. So when that happens, what you're, based on this idea up above here, what you're going to have, if this right here, if this d2 plus d3 over 2 is the center, it has to equal d4 plus d5 over 2, right? They have to equal each other. So I'll just write it out. If that's the design intent, right? That's the thing that we want. We could see that all we need to do right here is divide by 1 over p on both sides, right? And now n2 plus n3 must equal n4 plus n5. So here's another type of constraint that we might have when trying to pick out things. So here's a number of constraints, right? So we have some problem that we're trying to deal with, and we have a gear ratio that we know we need to achieve in order to get the desired output speed, or in some cases the desired output torque. And we're left also with these physical constraints. We're also this 10-to-1 thing we have to keep in mind. This also, by the way, that 10-to-1 is also relating to interference, right? We saw the other day with there's a really on the low side. We don't want to have too few teeth, because that kind of like has us have problems with interference. So that limits how small the pinion can be as well. So I think I've given enough introduction to this, and I don't know if there's enough time for an example. I've already talked too much, 16 minutes. I'm gonna break this into smaller videos. So I'm gonna make a new video for the next part of this. Sure.